Okay, here we go. And please feel free to jump in. The more questions, the better. So this is a rough outline of the material we'll try to go over. This first lecture is really just a broad overview. Some of the material in here, hopefully you already know, or maybe actually a lot of it. But I wanted to start off with a big picture overview, lots of movement and lots of images, and give you a sense of what you should be focusing on in the rest of the lectures. What is the overall context? What's important here? So I'll talk about the current state of gravitational wave astronomy, what's going to be in the future. Then that will take up about half this lecture. The second half will be specifically on gravitational self-force theory, which is how we model Emery extreme mass ratio wind spiral waveforms. As I'll show you, we can also use it to model things that are less extreme. I'll give you some evidence that it works pretty well even for current. Okay, we seem to have lost the video. Yes, by the end of this first lecture, you'll have an overview of the kinds of sources we're interested in and roughly of how we model them. Then in the final 4 lectures, I'll go step by step describing the key concepts that go into constructing these models. Some about black hole perturbation theory, some about how we deal with the small size of the small objects, some about orbital dynamics, so that's why I was asking if people are familiar with dynamical systems and Hamiltonian mechanics, really in particular dynamical systems more. Okay, and then the final lecture will focus on putting this all together and constructing the final waveform. And yeah, hopefully in that final lecture, you'll be able to produce a waveform on your own relatively easily. Okay, so big picture gravitational wave astronomy. So this is stuff hopefully everyone knows. I don't know if I have a laser pointer here. I'll just use the mouse. So basic story, we've got 2 objects orbiting around each other. These are the main kinds of sources we expect for the foreseeable future, just 2 compact objects, black holes or neutron stars, orbiting around each other, generating ripples in space-time. Again, it then gets detected by our detectors, in this case by LIGO. And the focus of this series of lectures will be about how we decode the waveforms we detect and extract information from them. So unlike a lot of experiments where you just see what you're trying to look at, here we just get wiggles, and usually those wiggles are buried underneath a lot of experimental noise. And so we need to be able to extract them and identify what created them, and the only way we can do that is with a very accurate model that tells you how a given waveform relates to a given astrophysical source. That will be the focus here. So another thing everyone here should already know, I'm old enough to remember when this was the distant future, and we were just waiting and waiting for the first detection of gravitational waves. In fact, when I was starting towards the end of my undergrad, and I was at a GR conference, everyone was talking about LISA already. This was 22 years ago. Everyone was talking about LISA and talking about how it was 10 years away. Then it kept being 10 years away, until it was canceled. And then it was no number of years away. That was when NASA pulled out because they were spending all their money on the James Webb Telescope. So NASA pulled out of the project. ESA didn't want to fund it by itself at the time. And so there were a few years where there was no plan for LISA. Then when it came back, all of a sudden it was 20 years away. I guess they'd gotten a bit more realistic during the cancellation period. And now we are back to 10 years away. So it's taken over 20 years to get to the same place I started at. Now, 10 years ago, the whole prospect of LISA became much more promising when we actually saw a gravitational wave with LIGO. And this was really one of the things that gave a big push to LISA because it suddenly seemed very viable that this could be done. So this was a signal generated by 2 black holes around 30 solar masses each. Ah, perfect, okay. Thank Thank you. Okay, so this was two 30 solar mass black holes orbiting around each other in basically, but okay, and as I mentioned, these signals are kind of buried within experimental noise. That's why we have a very, very noisy signal here. And the reason this waveform looks so messy, unlike the waveforms I'll show you later, is that it's kind of been convolved with instrumental noise to get looks like inside the detector. So this has three very distinct phases: an in-spiral, where the two objects are kind of far apart, gradually getting closer as they emit gravitational waves. The final merger, where they come into be just a single black hole. And then you have the ring down, where that single black hole vibrates, emits radiation until it settles down to be a Kerr stationary solution. So that was extremely exciting when it happened. You know, got multiple people the Nobel Prize. But then we started seeing these things all the time. Here I'm showing you all the detections in the first two observing runs, I think. Now we see them even much more often. So I just showed you all the signals that were detected over a 2-year span, and it was, I don't know, 20 signals or something. Now we've seen over 100, well over 100 now. We see them once a week or even more frequently when LIGO is actually up and running. And all of them look pretty similar. They all look basically like this, like a sinusoid whose frequency is increasing with time towards the merger. Then when the two objects merge, you get a spike, and then you ring down. And there's kind of a standard paradigm of how we model these kinds of signals. So early on, when the objects are far apart, we can use post-Newtonian theory. So post-Newtonian theory is a weak field, slow velocity approximation, so it works very well when you have objects widely separated, moving slowly. Then at the very end, when we have just a single black hole that's vibrating and emitting radiation, that's well described by black hole perturbation theory, because it's just a single black hole with small corrections that are radiating away. In the middle, in the merger phase, the only method we've got is numerical relativity, or at least the only first principles method is numerical relativity. So there you're solving the fully nonlinear Einstein equations on supercomputers, and you generate maybe one signal in a few days or a few weeks or a few months. So you can generate post-Newtonian waveforms in a few seconds, or actually much less than that. And same for black hole perturbation theory, but tying it all together with numerical relativity is a very expensive, time-consuming process. But that whole paradigm is focused on the currently observable signals. And in the future, we're going to have a lot more detectors that can observe a lot more things. So here are the currently operating detectors. The two LIGO detectors, Virgo in Europe. GEO 600 has been observing for many, many years, but it was never expected to actually detect anything. It was just a technology demonstration, and it is still not detecting anything. Then we have CAGRA, which also has not detected anything, but it is joining the observing runs and taking in data. They're still doing a lot of work trying to reach design sensitivity so they can start detecting. And sometime next year, we're supposed to have a LIGO in India that's just using the LIGO technology from America, shipped over here, and installed. And it's very important to have good coverage of the globe here, because the more coverage of the globe we have, the better we can locate where sources are in the sky. And so once we have LIGO India, then we will have pretty good coverage around the globe. But then also in 10 years, we're going to have LISA. So that's the space-based detector. It's going to be launched. The current plan is for 2035. I know it still says 2034 in some places and 2037 in some other places. The actual mission schedule is for 2035. Then we have another proposed but not funded project from Japan called the SIGO. We have two more space-based detectors proposed by China, Tianjin and Taiji. My understanding is that the plan is to just fund one of them, but they want both of them competing against each other for as long as possible. But So on Earth, we are going to get better detectors, what are called third generation or 3G detectors, the Einstein telescope in Europe and Cosmic Explorer in the US. Those will probably come a little bit after LISA, maybe late 2030s or 2040. But once we have this huge array of detectors, as I mentioned, we're going to be seeing a lot more signals and a much wider variety of signals. So here's a pictorial demonstration of that, or illustration of that. And I highly recommend you actually just go to this website if you haven't been there before, gwplotter.com. So this has the sensitivity curves for all the planned detectors and all the currently operating detectors over the full frequency range, and all the common sources they're expected to detect. So over here on the right, around 10 hertz or 100 hertz, we have advanced LIGO. So this is the noise curve of advanced LIGO. The advanced Virgo curve looks quite similar, not quite as sensitive, but similar. And here in red is that first signal that was detected in 2015. And you can see that was way above the noise curve. That was a very, very loud signal that we now realize we were very lucky to see so early on, because it was unusually loud, that it really just stood out above the noise. Then Einstein telescope is down here and at an order of magnitude greater sensitivity. So you can basically think of this as sensitivity. The lower, the more sensitive, and the higher these colored parts, the louder that signal. So detectors will be about an order of magnitude more sensitive. Then over here at a much lower frequency is LISA. So the reason LISA was so interesting and why people have been pushing for it for many decades now, it's not just 2 decades, it's 4 decades at least. The reason is that because it's lower frequency, that allows it to see heavier things. So you can basically think of just Kepler's law. The frequency of an emitted waveform is basically the same as the frequency of the orbit, the orbital frequency. Factor of 2 and some modulations, but it's basically just the orbital frequency. And in GR, just like in Newtonian physics, the orbital frequency, here I'm approximating it as the circular orbit frequency, looks exactly like this. Total mass divided by the cube of the orbital separation, all to the square root. So that's just Kepler's law, and it's still true in GR for circular orbits and for non-spinning bodies. In systems where the separation is not that much bigger than the size of the objects. We don't want them to be massively separated by parsecs or whatever. We want them to be pretty close to each other. And so then if you just take this capital R to be comparable to the total mass of the system, well, then you get the frequency is 1 over total mass. So the heavier the system, the lower the frequency. And LISA is designed to be in the millihertz range. The reason it can get to those low frequencies is that there's no noise coming from the Earth. So you can see at low frequencies, these ground-based detectors, their sensitivity is totally lost at low frequency because of gravitational gradients on Earth that we can't really get around. So in space, we will not have, and that allows us to go to much lower frequencies. And specifically at these frequencies, millihertz, what we're going to be able to see is massive black holes at the centers of galaxies and galactic cores. So they are usually around 1 million solar masses. So we will see massive binaries shown. Here's an example in blue. So these are 2 massive black holes merging. That happens when 2 galaxies merge, and then the black holes at their core also merge. But then we will also see these things, extreme mass ratio in spirals, shown here in green. So this is where you have 1 massive black hole in a galactic core, and then 1 stellar mass object, probably also a black hole, orbiting around it. It could be a neutron star, but most likely a black hole. And with these 2 kinds of very different systems, we expect to extract a huge amount of science from LISA. We will also have systems that start out in the LISA band, not massive systems, much lighter systems, that start out in the LISA band when objects are relatively light. but then they evolve to higher and higher in frequencies and eventually enter the frequency bands of ground-based detectors. So that's called multi-band detections. And that will also give us a lot of unique signs. The SIGO is in the middle here, in between LISA and ground-based detectors. As I mentioned, the SIGO is not funded, but it would really fill out this range beautifully. Then at very, very, very low frequencies, we have pulsar timing arrays. Pulsar timing arrays, because they're seeing such low frequencies, they see even heavier systems. So they see not massive black holes, but supermassive black holes with masses like 10 to the 9 solar masses. And they have detection of a background of gravitational waves from those kinds of massive, supermassive black hole binaries. Their detections haven't been with super high degree of confidence, but they keep building more and more confidence as they analyze the data for longer and longer and longer and take in more data. So with these different detectors, we cover most of the observable sources of gravitational waves in the universe. But with all these different sources, we need different methods. So I mentioned with current sources, we use post-Newtonian theory, we use numerical relativity. Those methods don't work so well for MRIs, or in general for systems with very large mass disparities, where one object is much bigger than the other one. So modeling has focused on comparable mass systems, which are over here. So these are the two most important axes in the binary parameter space. The mass ratio, this is the large mass ratio, so heavy object mass divided by light object mass. And then the orbital separation. So when the objects are widely separated, you have post-Newtonian theory. When the objects are very close to each other and also roughly equal mass, then numerical relativity is the only game in town. But then over here, where the objects are very close to each other, but not at all equal sized, here the method that is used, the only currently viable method, is called self-force theory. As you can kind of sense from the picture, the idea here is we are going to be perturbing the space-time of the large black hole due to the presence of the small black hole. So the whole system is treated as big black hole plus small corrections. Now, historically, the main thing that has driven the development of theory has been MRI. But really, numerical relativity starts to struggle with systems above mass ratio 1 to 15. It gets more and more expensive and takes longer and longer to run simulations when you have a bigger and bigger mass disparity. Basically, the simulation time is quadratic in this large mass ratio. So if it takes a few days to get the easiest waveforms we can get right now for equal mass quasi-circular, it would take 10 to the 10 days to get an MRI waveform. And that'll just be one waveform. We don't need one waveform, we need something like 10 to the 40 waveforms. So sometimes people ask me, how viable is it to push numerical relativity to MRIs? Probably never viable in the foreseeable future. And even at mass ratio 1 to 100, current NR codes, that's way out of reach to get a good waveform. You can get a not so good waveform with not so many orbital cycles, but we need a good waveform with lots of orbital cycles. And so perturbation theory, force theory, is more and more relevant because we're actually already seeing mass ratios around 1 to 25. And as detectors get better sensitivity, and as they're able to probe smaller frequencies, they'll see more and more ranges of mass ratios where you need to bring in a method other than post-Newtonian theory. So, long story short, we need new, accurate methods of modeling waveforms, specifically in this high mass ratio regime. You will hear me flipping back and forth between saying high mass ratio and small mass ratio. So that just depends if it's big mass over small mass or small mass over big mass. Anytime I say either one, I mean the same thing. And yeah, that's unfortunately very common in the community. We always just arbitrarily switch back and forth. Okay, so I want to run through the different kinds of binaries and say why each one is interesting and how we need to model them. So comparable mass binaries, the things we currently see. So I mentioned a mass ratio 1 to 25 that had been seen, but that's very, very unusual. And basically, the more extreme the mass ratio, the less of the signal you can see, because the further apart the objects get, the lower the frequency, and the higher the mass ratio, the lower the frequency. So with a mass ratio 1 to 25, we really only saw the very end. We didn't see a long in-spiral leading up. Now, Lisa will observe earlier stages of exactly the same binaries. Like I mentioned, this multi-band detection. We'll see the same binaries, but much earlier on when they're much more widely separated. Lisa will also observe massive, like I mentioned, two massive black holes merging. So with these kinds of comparable mass systems, we can get a lot of information, and we already have gotten a lot of information. So we can constrain the populations and histories of black holes. So we already know there are a lot more black holes than people had expected. And so yeah, I'm old enough to remember when people were predicting that neutron stars would be the common source of gravitational waves for LIGO. They were expecting, maybe thousands of neutron stars observed, and hopefully a few black holes. The actual situation has been exactly the opposite. We've seen a few neutron stars and many, many, many black holes. So partly that's just because black holes are heavier, so they create louder signals. But this has also changed our whole population models. And yeah, we now know black holes are very, very common in the universe. From the neutron star, we can also constrain neutron star equation of state. And that will be a big of 3G detectors, where they have much better sensitivity. And so when they do detect neutron stars, they can tell us a lot more about the constitution of neutron stars. We've also started to test modifications of gravity, violations of GR. Of course, so far we've only found that GR is correct. With 3G detectors and LISA, we'll be able to do that much, much better, get much more precise tests of our theories of gravity. Then, as I mentioned before, to model these systems, the early stages are well modeled by Newtonian theory, late stages are well modeled by numerical relativity. Then, because numerical relativity is so slow, and you need very, very rapid waveform generation for doing data analysis, basically, a single NR waveform takes a few days or a few weeks or a few months, and we need to generate waveforms in about a second. So NR is not the way to go for that. The way things currently work is you combine PN with NR. You use NR as calibration data, basically, and you use information about PN in the early stages. You combine that into full models that are fast. One such method is called effective one-body theory, EOB, which is probably the method that takes in the most theoretical information in how it combines these things. But there are also methods called NR circuits, which are just directly trying to replicate NR waveform without really a phenomenological or a theoretical way of combining things. Then there are models called phenom models, which use some EOB, use a lot of PN, but are a lot based on just looking at waveforms and seeing what is the important information to capture here, and then coming up with incredibly clever ways of reproducing intricate waveforms using almost no information, like very, very simple approximations work incredibly well. And phenom is incredibly fast. It's by far the fastest model that's available. But it's a whole family of models, phenom models. Okay, and the kinds of systems we're looking at in this case are these ones. This is mass ratio maybe 1 to 2, quasi-circular, very, very simple. And the reason all the systems we currently see are quasi-circular, or we think they're all quasi-circular, is that they've been around for quite a while by the time we detect them, and they lose eccentricity, they dissipate eccentricity as they evolve, and so they end up circularizing. And actually, numerical relativity puts a lot of effort, and that was a numerical relativity simulation I just showed you. Numerical relativity puts in a lot of effort to eliminate eccentricity. It's very hard for them to actually get down to the zero eccentricity that they want to get to. Whereas in the future, we'll be going the other direction. We want to include eccentricity. So these systems are quite simple. Not simple to model, but simple in terms of just appearance. Quasi-circular, roughly equal-sized. At the very opposite extreme, we have these emeries. And this picture doesn't really convey the extremity. This is mass ratio maybe 1 to 20 or something, but emeries are actually mass ratio 1 to 10 to the 5, or more likely 10 to 10 to the 6. So the smaller object is really basically just a point particle. It's so tiny compared to the big object. And these are one of the two main sources for LISA, as I showed. So the two LISA, massive black hole binaries, and emeries. Now what's interesting about these systems is that the small object takes a really, really, really long time to fall into the big black hole. Basically, 1 over the large mass ratio, or actually, sorry, mass ratio, number of orbits. So if you have a 10 solar mass object spiraling into a massive black hole, it's 10 to the 6 solar masses, you'll see basically 10 to the 5 orbits within the LISA band. And these orbits are not weak field. The small object is not spiraling in from very far away. In a detectable band, it's really close. So in fact, you think of Schwarzschild black hole. You have the ISCO, the closest approach you can basically get is 6M. Then for black holes, rapidly spinning black holes, and we do expect massive black holes to be rapidly spinning, that most stable circular orbit gets smaller and smaller until it reaches 1M if you have an extremal black hole. And we can have observable emeries that spend the entire observation time within 2 to 3M. We can have emeries that spend hundreds of years from 10M to plunge. These are kind of the extreme cases. Usually we would expect in the couple of years or 4 years of the LISA observation time, we would expect probably to go, the small object will go from 10M to merger. Probably. It depends on the mass ratio and the total mass. Okay, now these kinds of systems, to some extent, why we can't use the current modeling paradigm to model them. And we have to use self-force theory instead. You can kind of get a sense of the challenge just from this number of orbits. The number of orbits is extreme, and it's all in the strong field. Yeah, question? There will be changes in the waveform after the ISCO. You will get still probably a peak and then a decay, but with emeries, the signal to noise per orbit is going to be very, very small because it's proportional to the small mass ratio. So to get a big signal to noise, you're really relying on this huge number of observable cycles. And then the final merger for an emery is contributing a very tiny amount to the total signal to noise. And so you probably will not be able to say much about it from an emery. It's very different than short signals that we see today, where a lot of the SNR comes from the merger. For emeries, it's the exact opposite. Because you have so many cycles and because the per cycle SNR is low. Okay, yeah. Good idea, good idea. Yeah, so for the recording, the question was whether we can see the change in the waveform basically at merger for emeries, so after the ISCO, after the small object falls into the big black hole. And yeah, probably not. Although if we just look at the waveform ourselves, it's very observable there. Okay, so this is a movie I didn't see until I'd been working in this field for a long time already, but I really like to show it to people starting out. So this is a time-lapse video of the center of our galaxy, stars orbiting around the center of our galaxy. If you look really close at this white blob, you can see it's kind of zipping around something. And something, that dark something in the middle, is Sagittarius A star, the massive black hole at the center of our galaxy. And that is the kind of, not the kind of system we're going to be probing with EMRIs, but the kind of environment where EMRIs will take place. So this, actually I'm not sure if this particular image is the closest known star, but it's pretty close. The closest known star is around 400 M, and its closest approach to Sagittarius A star, to the big black hole, the star gets within 400 M, M being the mass of the big black hole. Whereas I just said EMRIs will have thousands, tens of thousands of cycles, hundreds of thousands maybe, from 10 M to merger. So on the scale of this image, you know, the whole scale of the EMRI is invisible. So it's so strong field, so close to the big black hole. I've already got it right here. So the EMRIs are way in there. Here I'm making it look like we're going to see an EMRI in our own galaxy. That's extremely unlikely. If we did, it would be amazing because it would be so loud because it's so close. But it's very, very unlikely. But the point is, for a typical galactic core like ours, EMRIs will be much tighter in towards the big black hole. And not those nice, simple Keplerian ellipses, but incredibly complicated orbits like this. So here's a movie of an EMRI. So as you can see, these systems are dramatically more complicated than the systems we currently see. There are resonances. Were they visible in the movie? I'm not sure. I don't remember. So I will talk about resonances probably in the fourth lecture, I think. But yeah, generically you have a very complicated, messy orbit, but then occasionally, okay, we're getting static from the speakers. Okay, but I'll go on anyway. Okay, yeah, so occasionally you'll get a more geometrically nice symmetrical orbit when an orbital resonance happens. So yeah, I'm not sure if we saw that happen there. Maybe we did. This movie was generated quite a long time ago, more than 15 years ago. It was using an approximate model, so you can't actually use this to generate your waveform today. But qualitatively, it's totally correct. This is what we expect inspirals in EMRIs to look like. You might have noticed the black hole getting bigger and bigger and bigger during the movie. You might have been clever and thought, it's absorbing gravitational waves and that's causing it to grow. No, that's not what's happening at all. The movie is just zooming in because the orbit is shrinking. The black hole does grow, but not nearly that much. It grows by an almost unobservable amount. Okay, so I said we were interested in these systems because you get so many observable cycles in the very, very strong field regime. But what do we hope to actually extract from all those cycles? So this is something that I think has changed a bit since I started. It used to be that EMRIs were really seen largely as a way of probing fundamental physics. and some astrophysics, but not the kind of super precise astrophysics you might think you could get from such a signal. So fundamental physics, the main thing that has been focused on is measuring the central parameters with incredible precision. So we expect to be able to measure mass and spin of the big black hole to about 0.01% error, and its quadrupole moment to about 0.1% error. Now, let's compare that to what we currently are able to do. So say with the Event Horizon Telescope. So the Event Horizon Telescope shows us images of that black hole at the center of our galaxy, Sagittarius A star. With that image, they are able to measure none of this. They can measure the mass mildly, but not that well. They can't measure the spin at all, and certainly not the quadrupole moment. So we're going to get incredibly precise information about just massive black holes. What do they look like? And because for a Kerr black hole, you have a unique relationship between all the multipole moments. So every multipole moment is specified by the mass and spin, given this formula. So this is the Lth mass multipole moment, the Lth spin multipole moment, and both of them are related to the mass and spin like this. So A is the spin parameter. Okay, so I'm told to point on the screen for the sake of the recording. Okay, so for a Kerr black hole, you have this unique relationship between all the multipole moments. Every multipole moment is uniquely specified by the mass and spin. So if you're able to measure the mass and the spin and the quadrupole moment, you can then test, does it satisfy this relationship? And therefore, is it a Kerr black hole? And yeah, we'll be able to do this test with much higher precision than any other planned experiment of any kind. So it'll be really the first case where we're really able to say, yeah, this is a black hole, and it's described by the Kerr metric. Then we can also do a lot of other fundamental physics tests. So we can measure new fundamental fields and charges. So typical modifications of GR, you know, you have an effective field theory description of modifications of GR, maybe motivated by string theory or something. You expect new fields to come in at some scale, often a scalar field, and then you can actually measure its effect on the binary. We can measure deviation from the Kerr quasi-normal modes. So the quasi-normal modes, those modes of the ringing when a black hole emits radiation and settles down to a Kerr metric, those are uniquely determined by the Kerr metric. And we can find deviations from the prediction for Kerr. Now, I already mentioned we're not going to see the merger ring down with any great precision for emeries. But if you have a highly eccentric source, it's possible for the small object to come by, zip past the black hole, excite quasi-normal modes to then ring down. So with each periapsis passage. And we might possibly be able to then measure those QNMs and measure deviations from Kerr. We can look for the presence or absence of an event horizon, additional wave polarizations in the signal, changes to the power spectrum due to modifications to GR. All of these things we can do with high precision with emeries. Okay, here I have an old statement I used to make, and I should probably remove it. So it used to be that people thought that emeries were going to be really like incredibly precise close to other things, because you have such a complicated orbit with so many cycles. And so your orbit is really, really sensitive to any little change, and therefore you think you can measure any little change quite well. And so it used to be said in the literature that the constraints on deviations from GR will generally be 1 or more orders of magnitude better than any other planned experiment. I think that's some of them is definitely true, but in general, this is probably a bit overly optimistic. In particular, people are starting to think more seriously about testing GR with emeries, and one problem with LISA in general is that if you're in an effective field theory description of modifications of GR, corrections come in with powers of the curvature. So corrections to GR are suppressed by powers of the curvature. And so if you're probing corrections to a massive black hole, well, its curvature is, dramatically orders of magnitude, many orders of magnitude smaller than the stellar mass black holes we see today. So in those kinds of effective field theory descriptions, the corrections to the big black hole are tiny compared to what they would be for a stellar mass black hole. So those kinds of corrections probably we will not be able to see with even the same level of precision that we will get out of a 3G ground-based detector, probably. For other kinds of corrections, we will way outperform everything else. And massive black hole binaries have the same issue. In that case, you have two massive black holes, both of which have very low curvature. But then also, people have started to focus more on corrections to the small black hole in an emery. So that's going to be a stellar mass object, and it will be corrected in the same way. If there is a deviation from GR, it'll be corrected in the same way as the stellar mass black holes we see today. But again, because there's so many cycles, we can collect more information about the orbit and possibly get better tests of GR than we would with ground detectors. Okay, then, as I mentioned, there's been a big shift over the last few years, kind of a little bit away from fundamental physics tests with emeries and towards high-precision astrophysics tests. So for a lot of astrophysics from emeries, you'll get valuable information, but you won't need high precision. So for example, we'll be able to constrain the mass function, the number of black holes with given mass, over the history of the universe. So that'll tell us a lot about evolution of black holes across cosmic time, and therefore also evolution of the cosmos across cosmic time. But for that, you probably don't need much precision in your measurements of the black hole mass. I mean, astrophysicists will be very excited if we can get any of these to 1%, let alone 0.01%. But there are other tests, other probes that people are now very excited about, which is probing the environment around massive black holes. So as I showed you that movie with stars orbiting around, those stars are all pretty far away, but there will probably be other black holes closer, and there's gas and plasma, and all of this will affect the observable signal. We don't know how much yet, it depends on your astrophysical model, but it's possible that we're going to be able to get direct measurements of properties of the accretion disk, direct measurements of the population of other objects around the big black hole through detections of emeries. And finally, if you measure a fair number of emeries, you can use them as kind of standard sirens, and you can measure the Hubble to about 1% precision we expect, which is broadly competitive with other types of cosmology experiments. Now, beyond comparable mass and extreme mass ratio, or actually in between them, we have a third type of system called an intermediate mass ratio inspire, or IMRI. So these can be seen both ground-based and space-based detectors, but in different variety. So ground-based detectors will see systems where you have one black hole that's a few hundred solar masses, and then one black hole that's, or a neutron star, that's maybe 100 times smaller. Whereas LISA will see, or could see, a case where you have an intermediate mass black hole of a few hundred solar masses or a few thousand solar masses falling into a massive black hole. And so these are cases where you have mass ratios of maybe 100 up to a few thousand. And these are mostly of interest because they contain intermediate mass black holes. So right now, we do not have a lot of evidence of intermediate mass black holes at all. We have tons of evidence of massive black holes in galactic cores and supermassive black holes. We have tons of evidence of stellar mass black holes. We haven't seen much in between those two extremes. We have various bits of indirect evidence, and we have seen one intermediate black hole in a LIGO signal that was formed by the merger of two smaller black holes. So that was the first real direct intermediate mass black hole with mass over 100 solar masses. Now, intermediate mass black holes are already kind of out of the reach of numerical relativity, but as I'll show you, they're probably within the reach of of self-force. So we would model them in exactly the same way as we model. Okay. So that's the big picture landscape that we want to situate ourselves in. Now for the rest of this first lecture, and probably I'm going to run out of time, but I'll try to finish all the slides today. So the rest of the first lecture, I'm going to be talking about how we model these systems using this method called gravitational self-force theory. So let me explain a little bit more why we really just cannot adapt current methods. So, as I mentioned before, these are highly relativistic systems. The entire observable signal will be in the very strong field. So post-Newtonian theory is extremely inaccurate in this scenario. Then you have this disparate length scales. The small mass and the big mass are separated by many orders of magnitude in their size. And so a numerical relativity simulation needs to be able to resolve both these scales simultaneously. And that increases the cost of numerical relativity simulation basically by a power of the mass ratio. Because your spacing has to be proportional to the mass ratio. Your time step spacing, you can't take big time steps if you have a small spatial scale in your system. Then we have this long in-spiral that's very difficult to handle. So I mentioned the number of cycles is proportional to the large mass ratio. Let me just motivate that. So the in-spiral is basically occurring at a rate given by the rate of change of the energy divided by the energy itself. So I'm dividing by the energy just to normalize it. The rate of change is proportional to the ratio. So it's a very slow rate of change. And the time scale is then inverse of the rate. So if the rate of change is the small mass ratio, that tells you that the time scale over which you in-spiral is 1 over that, meaning big mass ratio. So big M over small m. And therefore, you're getting roughly that number of the large mass ratio number of wave cycles. So around 10 to the 5 for the kind of canonical M-rays we consider. And that, in terms of numerical relativity, that gives you another factor of the mass ratio. So that's why I mentioned you have quadratic growth of runtime as you scale the mass ratio. So we need a model that maintains that very high precision over a huge number of cycles. Can't use NR, can't use PN. Okay, so we use gravitational self-force theory. And one thing I'd like to stress is how this relates to something very fundamental that we all learn about GR. So one of the first things you learn about GR is the equivalence principle. So the equivalence principle comes in different varieties, but kind of the simplest to understand is that if you take an object that's sufficiently small and sufficiently light, it moves on a geodesic of the surrounding space-time. So every object, no matter what its internal composition is, if it's sufficiently small compared to the ambient radius of curvature, say, and sufficiently light that it's not hugely impacting the space-time around it, then it moves on a geodesic. And that's why we all learn about geodesics as soon as we start GR, because every single object, if it's sufficiently small and sufficiently light, moves on a geodesic of the external space-time. And that is what Einstein used to verify GR looking at the precession of perihelion of Mercury. That is what Eddington used to verify GR using light deflection. It's study of geodesics in a space-time. But the key words there are sufficiently small and light. This is really just an approximation. It's a limiting statement. It's not a true statement about real physical objects. It's an approximation. In reality, every object, no matter what it is not rest mass. Every object has finite size and finite mass, affecting the space-time around it. So all of us here, every single thing is creating some small correction to space-time. And we all have finite size. So what we are looking at is very small corrections to the first thing we learn about GR, the equivalence principle or geodesic principle. So the way we're going to do this is we just deposit a small body into a space-time. Quite a lot of what I'm going to talk about actually isn't specific to emeries, although emeries are the most important example. But self-force theory is a more general approach to just treating a small object that's placed into some external space-time. And the idea is we take the exact metric and we want to approximate it as some external background metric that ignores the presence of the small body, plus corrections due to the small body. And here, epsilon is the small mass ratio, small mass over big mass. That's in the case of an emery. In some other space-time, it would be small mass over whatever external length scale is around. So we have a correction coming in at first order in the small mass, correction coming in at second order in the small mass, and so on. And I'll explain to you why I'm specifically stopping at second order as we progress. So once you've changed the space-time around the small body, well, multiple things happen. One is that little perturbation propagates away, and that's the waveform we detect. But another thing is, even in the neighborhood of the small body itself, the space-time is no longer the external background. There's little corrections due to the presence of the small body itself. Little corrections react back on the small body and drive it away from geodesic motion in the external space-time. And so we call that effect the self-force. So here I'm writing down the covariant acceleration in the background metric. If this were a test mass, the right-hand side would be 0, it would be moving on a geodesic, but instead we have little corrections to geodesic motion. So F1 comes from H1, F2 comes from H2, etc. And so these things on the right-hand side we call self-force, or in this case, self-force per unit mass. So if I were writing down Newton's law, I would multiply the entire thing by mass. In addition to self-force, on the right-hand side, we also get finite size effects. So every object has some finite size, and that couples to the external curvature around it to cause it to deviate from geodesic motion. And so those will be incorporated on the right-hand side here as well. In the second lecture, I think, I'll kind of briefly summarize how we derive this formula and how we formulate field equations for these metric perturbations. And the derivation is actually quite powerful because it's not just giving you corrections in binary systems, it's giving you the corrections to the geodesic principle in any space-time you happen to be in. And as a consequence, it actually serves as a proof of the geodesic principle. You find in deriving these F1s and F2s, the first thing you find is that the leading term is 0. There's no epsilon to the 0 term. And so that establishes the geodesic equation. And then we get corrections to that at higher orders. Now, as soon as you start writing down an approximation like this, the first thing you need to ask yourself is, how high order do I need to go for a given system I'm trying to model? You know, if you find you have to go to, yes? Yeah, binaries are probably the only ways we're going to see gravitational waves from bodies. So you need a non-zero quadrupole moment. You can have an object kind of zipping around, creating bursts of radiation, but you need some rate of change of a quadrupole moment. Not a time-varying one in that sense. If you had rate of change of acceleration, if you had things happening, dynamical things happening, which you always will in the universe, yeah, you would create some radiation. And so the sources that are closest to that would be hyperbolic encounters, where you have an object kind of just zipping around some other object, not orbiting, but just flying past. And it will have a little burst of radiation at closest approach. That's potentially observable. Not related to an observer. So if you have just a heavy object, it does not, because it doesn't have a time-varying quadrupole moment. So you need the time variation in addition to just having a quadrupole moment. And yeah, if you just have one object flying along, it's never going to have a time-varying acceleration to create radiation because it needs something interacting with it to cause that. Okay, so how high order do we need to go? We don't want to be in a situation where we find, you need to go to 10th order in the mass ratio to model MREs, because that would be totally hopeless, and we would just give up on the method immediately. We want to find that you can get good accuracy in a moderate amount of work. The first thing is, as I already mentioned, the in-spiral is very slow. It occurs on this time scale order 1 over the small mass ratio. So slow rate of change, long evolution time. Now, what I'm going to explain is why I'm specifically going to second order. Why do we need this second order term? So suppose we neglected this second order term. We would then have an error in our acceleration of order epsilon squared, because we'd be throwing away this term. Now, if you just very naively integrate twice, you just pull up the t squared from the bottom, move it to the right, this error in the acceleration is going to lead to an error in position of order epsilon squared times time squared. And if we're looking at time scales of order 1 over epsilon, well, this error in the position is of order 1. And if you have an error of order 1, that's unacceptable for gravitational wave source modeling. So this order 1, this could be 10m, this could be hundreds of cycles. It's just something that doesn't depend on the mass ratio, so it could be anything. But in particular, we have no reason to think it's small, and we actually know now experimentally that it is not small. So accurately describing the orbital evolution requires going to second order in perturbation theory, means solving the Einstein equation through second order in the small mass ratio. The same argument here tells you that if you omit third order effects, you have an error of order the small mass ratio in the orbital position, but that also then translates into error of order epsilon in the waveform phase. So that at least guarantees that if your mass ratio is really, really small, you don't need that correction. So you don't need to go to third order, second order should be enough. So we say that second order is probably necessary and sufficient for good waveforms. Now to explain cell-force theory and how we generate waveforms, it's always most useful to start at 0th order, forget about the Einstein equations, forget about the metric, or at least the metric perturbations. Just think of the 0th order case, which is a test mass moving on a geodesic in Kerr. So we expect the big black hole to be a Kerr geometry, a Kerr black hole, or possibly to be Kerr plus small corrections. So we expect it to be very close to Kerr. And so the first thing we study is just motion in Kerr, geodesics of Kerr. As you can already see, these geodesics are extremely complicated. They are not the nice simple Keplerian orbits we learn in Newtonian physics. They're not even the nice simple orbits we see in current models of ground-based detectable systems. But they are still what we call integrable, meaning they have enough constants of motion to do what we call reducing the system to quadrature. Really all this means is we can, in principle, analytically write down the solution. So we have 3 constants, or 4 if you count the small mass of the small object. We have 3 constants of motion. We have the energy, we have the angular momentum, and we have the Carter constant. So this angular momentum has a little z on it. This is the angular momentum of the orbit around the spin axis of the big black hole. So by convention, we always say the spin axis of the big black hole is the z-axis, and then Lz is the orbital angular momentum around that. Then we have this third constant called the Carter constant, which is related to the orbital inclination. So you can see, unlike Keplerian orbits, this orbit is not to a plane. Also, unlike orbits around a Schwarzschild black hole. So in the Schwarzschild case, you can have complicated orbits, but they're all confined to a plane. Here, it's not confined to a plane. The whole plane of motion is vibrating up and down like this. And the extent to which it moves up and down like this is dictated by the Carter constant, Q. So this happens when the orbital angular momentum is not aligned with the spin axis. If the orbital angular momentum is aligned with the spin axis, then the motion is confined to a plane. But as soon as you have any little misalignment between the spin angular momentum of the big black hole and the orbital angular momentum, then this whole plane will precess up and down like this. So because of that, generically, these geodesics are tri-periodic, meaning they have three distinct independent frequencies or periods: radial, polar, and azimuthal. So radial, the thing is moving in and out, like you'd have an eccentric orbit even in Newtonian physics. It's getting to a closest approach, back out to a furthest approach, and back and forth. Then, as I mentioned, the whole plane is precessing up and down. So you have a polar period, and you have an azimuthal period just for motion round and around the spin axis. You have three independent periods. If you have a resonant orbit, two of those periods become dependent on each other, meaning they are related by a rational ratio. So that's a very special case. Generically, you have three independent frequencies. So we can rewrite the geodesic equation in terms of nice variables, like these energy, angular momentum, and Carter constant, and like these three phases. So you have three periods of motion. For each of those periods, you can define a phase that runs from 0 to 2 pi along one complete oscillation. And you can define these phases such that they have constant frequencies. So the rate of change is some frequency that's uniquely specified by these three constants of motion, together with the mass and spin of the big black hole, and yeah, that's it. So despite the very, very complicated motion we observed there, we can simplify things dramatically. These variables are what are called action angle variables. If you remember that from, yeah.
We can have similar kind of orbits when we have spin precision for poor mass cases, right?
Yeah, so this is spin precession in a different language, yeah.
So can we say, like, then can we project this in NPN when we have spin precision and eccentricity? Then only can have a similar kind of picture.
Yeah, so it's similar. It is similar. So the same qualitative dynamics. So yeah,
This is not true for this one, right? Can have this kind of thing without.
This is spin precession in a different language. So spin precession means orbital angular momentum is precessing around a different spin axis. That is what's happening here. The orbital angular momentum is precessing around the spin axis of the big black hole. So this is spin precession.
This kind of motion that we have, we're not getting for non-spinning cases.
This motion you don't get for non-spinning cases, yeah. So if the big object is a Schwarzschild black hole, you don't get this. If you put spin on the secondary object, which you do need to if you want to go to second order, then even if it's a Schwarzschild, even if the big black hole is a Schwarzschild black hole, then you'll have precession of the spin of the small object around its own orbital angular momentum.
So it's for Syria as well, for non-spinning cases, all the orbits are equal to.
Yep. Yep. Okay, so these variables are what are called action angle variables. I won't actually talk about the real action variables. I'll just think of these constants of motion as equivalent to action variables. And then the important thing, these phases. Three constants of motion, three phases. So the very complicated geodesic equation you can reduce to the statement that dj dt is 0 and d phi is omega. And so that'll be very important once we discuss how we actually model these things. Okay. Now let me return to this question of how high order we need to go and make it a bit more quantitative. So in about 2008, Hinder and Flanagan developed a 2-time scale analysis of the orbital motion around a Kerr black hole. So this is orbital motion once you turn on a self force. Once you turn on the self force, those things that were constants are now going to slowly evolve. So the energy, angular momentum, and Carter constant are no longer actually constant. They're slowly evolving. They evolve on what's called the radiation reaction time, which is 1 over epsilon. So it's the same evolution time scale I mentioned before. And then we're in a situation where we have 2 distinct time scales. We have the time scale over which these parameters are changing, but then we have the orbital time scale on which the small object is just zipping around. And that's independent. That short time scale is independent of the mass ratio, so epsilon to the 0. So on this long time scale, what Hinder and Flanagan showed is that the orbital phases, or the waveform phase, has an expansion that looks like this. So here, I'm expanding for small epsilon, and what I'm holding fixed when I do that expansion is not ordinary time, it's slow time, meaning epsilon t. So on a very long time scale, epsilon t is of order 1, because t is of order 1 over epsilon. So the leading term there, phi 0, comes with a 1 over epsilon. That's because the longer time you wait, the more signal you accumulate, the more phase you accumulate. And if you wait a time of order 1 over epsilon, then the amount of phase you accumulate is also of order 1 over epsilon. Then we have a correction that's epsilon to 0, and then so on to higher orders. And when we ask ourselves, what order do we need to go to get a good model? Well, it looks like this is the order to go to. The most important thing we need to track is the waveform phase, which is very closely related to the orbital phase. And this is saying that if we keep these first 2 orders, we're okay because the next order is order epsilon, which for mass ratio 10 to the 5 is 1 over 10 to the 5, so very, very small. Yeah. So that's what I just said. If you wait a time of order 1 over epsilon, you're accumulating a phase of order 1 over epsilon. So the phase is accumulating roughly linearly with time. So the longer you wait, the more phase. Okay, so we expect these 2 orders are good enough. And I'm going to introduce some nomenclature here. So they said something that gets you this first leading order is called adiabatic order. And so that comes from a kind of an older picture where you're thinking of geodesic orbits adiabatically evolving from one orbit to the next, to the next, to the next, to the next. And that's called 0PA. And it's determined by the averaged dissipative piece of the first order self force. So a very specific piece of the first order self force. So you do not need the whole first order self force to get the adiabatic order phase. Of course, you also need to know a lot about the geodesic dynamics. So it's kind of geodesic dynamics as well as first order dissipative. Now to go to the next order, which we think is what we need, so that's called first post-adiabatic order. So the order counting that Hinder and Flanagan are using here is orders beyond adiabatic. So this order is determined by, well, the rest of F1. So you now need all of the first order metric perturbation. You also need all of the first order, sorry, wrong way around. You need all of the first order self force and all of the first order metric perturbation. And we now need some information from the second order self force and therefore from the second order metric perturbation. So we need all of F1 and some dissipative piece F2. And so this is kind of the guiding philosophy in the community and has been for quite a long time, that this is the goal. to get everything at first order and to get just enough at second order. And this has been the guiding goal for maybe 15 years. But this study actually goes back way, way, way before that. People have been looking at the motion of small objects around black holes for a century. They might not have thought of it as a black hole in 1910, but nevertheless, they were solving the geodesic equation in Schwarzschild spacetime. That's exactly the starting point we were starting from. So that was done already in the 1910s. In the 1970s, people started to look at radiation emitted by a small object orbiting around a black hole. So the work of Tucholsky, the work of Detweiler, and others. And this gives you what are called test mass waveforms. So there you put a particle on a fixed geodesic orbit. Back then they were really only considering circular orbits, so you have a particle just moving around in a circle around a Schwarzschild black hole or a Kerr black hole. And the waveform you get out looks something like this. You have a first order amplitude. We decompose into some set of spherical harmonics. I'll discuss different harmonics tomorrow, hopefully. You decompose into some set of spherical harmonics. You have some amplitudes that depend on just the radius of the orbit, or equivalently, the frequency of the orbit. And then you have this phase factor that comes with an omega t, so a frequency times time. And these start at L equals 2, quadrupole order. And then what's determining the time dependence here is, well, the fact that the frequency is constant, so it has no rate of change. So these amplitudes are all constant. And then the only time dependence is coming from this phase factor, which is just exactly proportional to the orbital frequency. So here I've drawn the nice circular orbit in Schwarzschild, and here is the waveform that comes out from the particle. So this was already considered back in the 1970s. I don't think people had the computing power to easily, actually get this waveform out, but they did look at, gravitational wave fluxes emitted by waveforms like this, fluxes of energy. And they were also considering adiabatic inspirals, so 0 PA inspirals in waveforms, although it wasn't fleshed out in any kind of detail back then. So in that case, let's just compare what we got. So at this test mass waveform, we have a constant set of amplitudes, and the time dependence here is just omega times t. Now, once things are evolving, the frequency starts evolving with time. The orbital frequency starts evolving with time, slowly, but evolving. And so what happens is these amplitudes are now slowly evolving. They're functions of a slowly evolving frequency. Now, rather than just omega t, we now have the orbital phase. So if the frequency were constant, then omega t would be the orbital phase. But instead, the frequency is slowly evolving. So now our orbital phase, the p here stands for particle. So I've got a particle going around in a circular orbit. So the rate of change of the particle's phase, orbital phase, is this frequency. The frequency itself is now slowly evolving. And you can get a very simple way of extracting the rate of change of the frequency itself using an energy balance argument. So you say that the frequency is a function of the energy of the orbit. The energy is slowly dissipating away because we're emitting gravitational waves. So the rate of change of the frequency is the rate of change of the energy multiplied by d omega dE, so just chain rule. Then dE dt is equal to, by energy balance, is equal to the emitted gravitational wave energy. So the energy that's emitted out to infinity, curly f infinity here, plus the energy that actually falls into the big black hole. So the sum of those two fluxes, we call them, is equal to the rate of change of the orbital energy. This is only true at leading order. So we then get a fairly simple formula in terms of geodesic quantities. So dE d omega, or d omega dE, is just a geodesic formula. Then we have these fluxes. These fluxes we can calculate actually from these amplitudes, h1, but these amplitudes are just a function of the frequency. So in fact, we can go back to the previous slide and we can calculate those amplitudes using information we got from the geodesic case. Because these amplitudes are exactly the same. These h1s are exactly the same for the geodesic as for the evolving orbit. The only difference is that the frequency is evolving in the one case. But as a function of frequency, it's the same. So once we turn on dissipation, the particle falls in, as you see in this picture, and the waveform is now changing in frequency with time and also in amplitude. The amplitude is growing and the frequency is growing. And so this waveform, hopefully everyone will be able to generate themselves by the end of the 5 lectures. And with a reasonably powerful laptop, it only takes a few minutes. Okay, so that was kind of the leading order case, adiabatic, and so the simplest physical scenario, circular orbits around a Schwarzschild black hole. But that is kind of the picture we take forward from here, where you have slowly evolving things, you have rapidly evolving phases, you pre-compute a bunch of things. So I mentioned we calculate those h1s as a function of frequency, we pre-compute a whole bunch of those, and then you can generate your waveform. And the generation of waveforms is actually very, very quick once you've done your pre-computations. So going back to the early 90s or mid-90s, people were already thinking of, okay, we got to go beyond that. We got to do better than that because LISA is 10 years away. That was 1996. So they thought we need to do more proper perturbation theory. We can't rely on these simple energy balance arguments. We need to actually go to higher order. We need to calculate self-forces, etc. So Mino Sasaki Tanaka in early 1996 derived a formula for the first order self-force that's created by a metric perturbation due to a particle. So it's a function of not the full metric perturbation produced by the particle, but what's called the regular piece of that metric perturbation. I'll explain that in more detail tomorrow. Just a few months later, the same year, and Wald derived the same formula using a different method. And so now we call this leading order equation of motion the Misa-Takwa equation. Mino, Sasaki, Tanaka, Quinn, and Wald. Then it took about 10 years to actually go from this formula to a method of calculating 0 PA, so still leading order, waveforms for generic orbits around Kerr. The reason this was tricky is that simple energy balance arguments do not extend to these precessing orbits. So they actually had to start from the self-force equation of motion and from that derive what the 0 PA evolution is for a generic orbit in Kerr. And yeah, a few different groups got that. But nobody was yet ready to actually implement that. It took a long time to get implementations of that. Then, a few years later, a few of us, including myself, derived the second order extension of this formula. So the order to which we think we need to go. But then it still took a few years more to actually implement that. So 2005, we had a method of calculating adiabatic waveforms for generic orbits in Kerr. It wasn't until 2021, 15 years later, that people actually calculated those waveforms. So that was the first year where we had the first 0 PA waveforms for generic orbits. That same year, myself and collaborators got the first 1 PA waveforms, so second order perturbation theory waveforms. That was not for generic orbits in Kerr, that was for quasi-circular orbits around a Schwarzschild black hole. So you can see kind of the time scales involved here. 1910s, we had geodesic motion around a black hole. 110 years later, we are now at the next order beyond that. Okay, so here's an example of the kinds of waveforms we see from these generic orbits in Kerr. I haven't introduced this acronym. I'll get back to that a couple slides from now, I think. Okay, so there's now a few different ways to calculate generic orbits in Kerr, or generic inspirals in Kerr. we have a fully numerical method. That has only been used to generate a few waveforms, but it should be that we'll have complete coverage of the parameter space and rapid waveform generation at 0 PA order for generic orbits probably the next couple of years, maybe even a year. Separately from that, we have high order post-Newtonian approximation, where the idea is you start from 0 PA infrastructure, 0 PA equations in self-force theory, and then you expand everything in weak field and small velocity limit. And so we have analytically 0 PA waveforms in this approximation. What I'm showing you here is actually the analytic one. I'm showing you two. One is the analytic one. One is actually what I call the test mass waveform. So no evolution, it's just fixing a geodesic orbit and reading off the waveform from that geodesic orbit. And you see on this very short time scale, you can't really tell the difference. It's only on the long time scales that you really see the impact of evolution. Okay, so that was the state of the art in 0 PA waveforms. Then at the same year, as I mentioned, we got the first 1 PA waveforms. And so the first question we had was, are these waveforms correct? Have we done everything correct? We now know we actually didn't, but it turned out to not matter. Actually, even at the time, we knew we were doing one thing wrong. Now we know we have done multiple other things wrong. But none of them seem to have any impact on this waveform. So first thing was, is this correct? How do we test whether it's correct? So we can compare to post-Newtonian theory, but that's only weak field, or we can compare it to numerical relativity. Now we only have numerical relativity waveforms to compare against when the mass ratio isn't so extreme. So that's what we're comparing against here. This is mass ratio 1 to 10. We have done comparisons against many different mass ratios, between 1 to 1 up to 1 to 15. In orange, this is our 1 PA waveform, and then in blue is the numerical relativity waveform. And so you see, we're doing pretty well. We have some dephasing right towards the end, and then our waveform, with our current method, our waveform just cuts off before the ISCO. So we actually currently don't evolve past the ISCO with this waveform. But as I mentioned, that's not super important for MRIs anyway. Okay, so here we see that we're doing pretty well. We see maybe 0.2 radians of dephasing at the end here. And this is mass ratio 1 to 10. So if I had predicted this 20 years ago, numerical relativity people would have said, what the hell are you talking about? This is nonsense. You're not going to get this level of accuracy with a perturbative scheme. You need full GR for this. But here it is. And really, actually, people should have expected roughly this. Because, as I mentioned, the phase error is of order epsilon. Epsilon is 1 over 10 here, and our phase error is of the order 0.1 radian. So it's actually exactly what we should have predicted. But if you spent 20 years solving the fully nonlinear Einstein equations, you tend to be skeptical of approximation methods. Okay, so that's the kind of surprising if you're an NR person, domain of validity. So I showed this cartoon before of the different regimes, different models work in. A few years ago, Martin van der Ment and Harold Pfeiffer did a more quantitative study of where the different boundaries lie between different regimes. This was before we even had 1 PA waveforms, so they were predicting the accuracy of 1 PA waveforms by looking at a whole bunch of numerical relativity waveforms and doing a kind of a fit. We now know, now that we have 1 PA waveforms, that this picture was overestimating the accuracy of self-force a little bit. Although I also mentioned that we made mistakes, so it's possible that once we correct those mistakes, we'll recover this picture. So this is to be compared with this, same axes basically, same different regions. But now I've put numbers on the x-axis and numbers on the y-axis. And so the numerical relativity simulations they were looking at were down here, in the bottom left, like in the previous cartoon. Post-Newtonian theory here, the way that they were setting this up, they were integrating kind of from the infinite past towards merger. And so post-Newtonian theory starts up here and then goes down. And then self-force, at 1 PA order, covers most of the parameter space. And these numbers here are telling you their desired level of accuracy, and so that's why you get different regions telling you where different models are accurate. Okay, so self-force appears to cover a lot of the parameter space. Self-force also has a very different paradigm for modeling waveforms. So I mentioned the paradigm that's currently used for ground-based detectors, which is we generate a whole bank of NR waveforms with different parameters. Each one of those waveforms takes a huge amount of power, like computing power, but literal power. They all have to budget for energy usage. It takes a long time to get these waveforms, but then you need a model that generates waveforms in a millisecond, like nothing. And so we construct fast models. Well, I don't, people do. Construct fast models that are informed by PN and calibrated to NR. And they're just trying to reproduce NR as well as they can, as well as having the correct limit to PN in the weak field. And so that's the methods I mentioned: effective one-body models, NR surrogates, and phenom models. So the paradigm in self-force is totally different. Because in self-force, our method of solving the Einstein equations is also our method of generating rapid waveforms. So when we solve the Einstein equations, we are actually getting direct inputs for our final waveform model. It's not the case that we generate a whole bunch of waveforms and then try to concoct some approximation that reproduces them. No, we are getting our waveforms directly from the Einstein equations, but we're getting them in this particular way where we solve field equations again and again and again and again and again to get inputs for the waveform. Then once we've solved that and we've got all the inputs pre-computed and stored, then we can generate a waveform basically instantly. And so I'll describe that in the next lecture. And so most of the community has really coalesced around this software package, Fast Emery Waveforms. So it does exactly what I just described. It takes pre-computed data from the community, and from that pre-computed data, it can just generate waveforms instantly. Okay, maybe not instantly, 10 to 100 milliseconds, but it's possible that in the near future, that'll be sped up by probably a factor of 10. And so yeah, everything is kind of funneling into this few software package right now. Okay, so I'll wrap up there, only a little bit over time. Okay, so just some things I want you all to keep in mind while we go through lots and lots of technical details in the coming lectures. So first thing, of course, is that IMRIs and EMRIs are going to be increasingly important for gravitational wave science. And actually, to give you a sense of the time scale, the LISA mission wants realistic waveforms from the modeling community by 2030. We're not going to have realistic waveforms to give them by 2030, but that's what they want. So it's actually not 10 years away that we need these waveforms. It's very, very soon. Now, the other thing is kind of thinking where self-force is. And it's very complementary to existing methods, or to more developed methods, PN and NR. It's the only known method of obtaining highly accurate waveforms for really small mass ratios. And it seems to cover a surprisingly large amount of the binary parameter space. But also, on a more theory level, it really connects to something very, very basic that we learn right away as soon as we learn GR, which is just a little object orbiting around a black hole. And we're just doing that with more and more accuracy. And kind of the tagline for self-force waveforms: everything we're doing is first principles. We're solving the Einstein equations to get our waveforms, but also the ultimate waveforms we get are fast, which is very different from the NR-based paradigm. Okay, so again, just a preview. We're going to cover next perturbation theory in GR, specifically in black hole spacetimes. We're then going to do how we introduce a small body into a spacetime, because the small length scales always introduce problems. Then we'll study orbital dynamics, and then the actual waveform production. And now in the title of my series of lectures, there was the words tidal effects. I wasn't sure what was I was supposed to be covering on that, but I'll discuss with the organizers. So I might insert some tidal things in this last lecture. But actually, even in lecture 3, there will be a little bit thematically related to that. Okay, so we will wrap up there. And yeah, I'll also discuss with the organizers how to get you that Mathematica software I mentioned, and we'll start referring to it starting tomorrow.